Okay, welcome everybody to lecture 23 of CSE 548, the analysis of algorithms. Let's start off, first of all, are there any questions about anything in the course material, any logistical issues, anything else come to rise? Okay, since we last spoke. Okay, the subject we started covering in the last lecture is the theory of NP-completeness. And in order to understand the theory, really there is only one idea that we're going to be using. Okay, and it's a simple, and sometimes it's a simple enough idea that anything interesting about it can fit on this one slide. Okay, so the single most important thing to understand about the theory of NP-completeness is the following idea, which I talked about last time. I'd like to repeat one more time. Okay, suppose, let's say, that we wanted to find an algorithm. Okay, suppose I gave you the following algorithm to solve a problem that we call the Bandersnatch problem. What is the Bandersnatch problem? It's just the name of a problem. Okay, one way we could solve the Bandersnatch problem is to take the problem, do a translation from the input of the Bandersnatch problem into a format such that it's an input to another kind of a problem called the Bobilli problem. Okay, what's the name of the Bobilli problem? Again, just the name of a different problem. But we're doing this translation in a very special way. First of all, the format has to change because the input for Bobilli might be a lot different. But we're doing this translation in such a way that the answer to Bobilli on the translated instance is the same as the answer to Bandersnatch on the original instance. Okay? If that's true, then if we want to solve Bandersnatch sub g, what we can do is do the translation, call a Bobilli subroutine that solves the translated instance. And since we did this translation such that the answer to this is the same as the answer to that, once we know the answer to this, we can simply report that as the answer to the problem that we had in mind. Okay? My claim is if I can do that translation, I have a correct algorithm to solve the Bandersnatch problem. Okay? Any questions about why it's correct? Okay? It's important to see that the magic here is in this power of this translation. It's not just any translation, but it's a translation that preserves the answer to the problem. Okay? If I've got an algorithm like this, what is the implication of this? If I give you a fast way to solve Bobilli problems, and my translation routine is fast, then the Bandersnatch algorithm, this Bandersnatch algorithm, will have to run fast. Why? Because it's fast plus fast is fast. Okay? That should be obvious. Okay? If this is a correct algorithm and all the steps run quickly, okay, this gives a fast algorithm. A fast algorithm for this will follow from a fast algorithm for Bobilli. But likewise, if I have a lower bound on Bandersnatch, or I know Bandersnatch is hard for some reason, okay, that Bandersnatch would in fact take exponential time, no matter how you run it. It's hard under any possible definition. Okay? I can give you an algorithm like this, meaning a way to translate from Bandersnatch instances to Bobilli instances. The hardness of Bandersnatch would imply the hardness of Bobilli. Okay? Because if it's hard to solve Bandersnatch, okay, that there's no algorithm known for Bandersnatch, can't possibly be any algorithm known for Bandersnatch. If you give me this algorithm, okay, and we know how fast it is, except for the subroutine for running Bobilli, we know that any Bobilli subroutine that works correctly has to run slowly, okay, has to take exponential time. Because if it takes exponential time to solve this problem, and we have an algorithm whose time depends upon this for solving it, this problem has to be slow. And that's the idea that we're using to prove hardness. Okay? We're going to start from a problem that we know is hard, okay? And then, for a problem we don't know the answer to, we're going to show how to construct the translation, okay, so that we convert one problem to the other and prove the hardness of mobility, assuming the hardness of Bandersnatch. Okay, any question? Yes?
Can the translation be slow?
Okay, now the question is, can the translation be slow? If the translation is slow, okay, we've proven nothing. Okay? But if you think about it, you're going to be describing the translation. Okay? So you're explaining, in some sense, how to do the translation. If the translation is slow, you're not interested. You know you've proven nothing. But since you're specifying the translation, you can analyze the time of your translation and prove that your translation is fast. Okay? So that's something that's going to be in our control. What we're going to be saying is we start out with a problem that we know is hard. Okay? You have a problem you want to prove is hard. If you can describe a translation procedure, okay, and you show that that translation procedure is reasonably fast, okay, something less than exponential time, then you're in business. Yes?
Can we do the other way around? So we start with the problem we have to prove and show that there is a phenomenal translation to the problem that we know that we can complete.
Okay, so you're saying what happens if the hard problem is here? You're saying here we have a known hard problem. Here we have a problem you don't know anything about. Okay? You describe a way to translate from the problem that you don't know about, go through a hard problem. Okay, your translation may be fast. What will you have given as a result of that? No. You would have given yourself a slow algorithm for solving Bandersnatch. That's what you would have given yourself. If you know mobility is a hard problem, and you explain that a way to do Bandersnatch using the hard problem, all that you have done is give a slow way to solve Bandersnatch. It's like, if I want to walk from here to the other side of the room, how hard is that? Okay? Well, if I attempt to go through this wall and walk around the earth the other way, it's a very hard problem. Okay? If I start banging into that wall, have I proven it's hard to walk from here to there? No, I've just given a hard way to do it. That doesn't mean there isn't an easy way to do it. Okay? So you haven't proven anything if your hard problem is here. All you've said is, I have come up with a slow algorithm for solving this. What you want to do is to take the hard problem and make the hard problem here. Show how to solve the hard problem in terms of something that you don't know for sure is hard. And if you do that, then you've proven that problem has to be hard. Okay, question?
Does it mean that the translation from Bandersnatch to Bobili is it's only a one-way translation?
The translation, what about is the translation from Bandersnatch to Bobili? All you need to do is to give a one-way translation.
Because
so it translates instances of these into instances of those with a special property.
Bobili was hard, and there was a way of doing Bandersnatch easy. We could translate Bobili to Bandersnatch and do it easy way.
So you're saying is that if Bobili was hard, okay, it's possible that there was another. I'm a little confused what you're saying. If we know Bobili is hard, and we take Bandersnatch instances and translate them into Bobili, all we are giving is a way to solve Bandersnatch via Bobili. But Bobili might, if it's hard, then you've given a slow way to solve Bandersnatch. You have not, it doesn't mean there isn't a fast way. Just like when you give me tell me in a class that you can't find an algorithm, fast algorithm for this problem. That does not mean the algorithm does not exist. Okay? What we're doing here is coming up with a way of proving that no such algorithm exists. Because we're going to know Bandersnatch is hard. Okay? And the soft problem, the problem we don't know about, is going to be going here. Okay? Any questions about that? Yes, question.
Yeah, basically here, Bandersnatch is the problem we know. It's hardness, right?
Right.
And the mobility is the problem we want to know.
So Bandersnatch is the known hard problem. This is the guy that we know is impossible to do quickly. We're trying to come up with a tool to prove that mobility can't be done quickly. And this is a way to do it. Okay? I haven't actually gone through any examples yet, so maybe it'll be clearer later on when we show some examples. Okay, what we mean by a translation, that's clearly where the magic is. But the important thing to see here is that we're translating one problem to another and to see why the hardness is implied. If this guy is hard, okay, and we don't know about this guy, but we show a way to do the guy we don't know about. We can do the hard problem if this guy can be done easily. Then, since we can't do this easily, we can't do that easily. That's the implication. Okay, and it's kind of a backwards way of looking at it. Okay? How many people think they got it? Okay, how many people don't think they got it? Okay, any questions from the people who don't feel they got it yet? Question?
Well, what's the, I mean, is it just a good faith assumption that the Bandersnatch is hard?
Okay, now the question now is, where do we start from? Okay, why should I know that Bandersnatch is hard? Okay, if you were a trusting soul, it'd be because I told you. Okay, but better than that, we'll later go on to see that there's good reasons why certain problems are known to be hard. Okay, and we'll get into that a little bit more later. That's actually an interesting question. Okay, question.
Mobility problem here, we cannot convert it to an easy problem, to another easy.
So what we're doing here is this. If Bandersnatch is hard, and we go through this translation, we've proven mobility is at least as hard as Bandersnatch. Okay, that's really what we've proven. Because if we could solve mobility, we could solve Bandersnatch. Okay? So that's what we're proving. This guy's got to be at least as hard as that guy. Okay? Because we can do that guy if we can do this guy. Okay? Any other questions? Let's try some examples. Well, let's try a little bit more exposure. But when you're confused, okay, go back to this slide and rethink it. Think about why we're coming up with an implication. Why we're implying hardness based on an algorithm like this. Okay? That's questions. Okay. So now if we're doing translations, in some sense the heart of NP-completeness theory is this art of coming up with these translations, these reductions. So if we're writing, really what you're going to be doing now is specifying an algorithm, a translation procedure for one problem to another. So we've got to be careful about what we mean by a problem. Okay? And again, when we've talked in general this semester about problems, a problem is a general kind of a question, okay, where we have certain slots for what kind of input we're expecting and certain conditions on what we expect the output to be. Okay? So for example, one of our favorite problems was the traveling salesman problem, okay, where we took as input a weighted graph, okay, and asked ourselves what order of the vertices would minimize the sum of the edges traversed there. Okay? This is a well-defined problem. Now, note that there's a separation between what we mean by a problem and an instance. An instance is the particular data you give to the problem. Okay? So, for example, here is a graph. This was a weighted graph. This weighted graph is an instance of the traveling salesman problem. Okay? Sort of just the distinction between program and data. Okay? A problem is in some sense described by a program, an algorithm that solves that problem. Okay? Whereas an instance is simply the data that you feed into that program. And of course, a program is correct if it works correctly on all possible instances. So what is it that we are doing when we talk about translating one problem to another? What we're really looking for is a procedure that will translate the input instances of one problem into the input instances of another problem. So what is it that you would expect if you were going to try to do a translation from traveling salesman to something else? What is it that you're going to be translating? Okay? You're going to be translating graphs. Okay? The input, okay, of this kind of a problem, which is going to be a specific graph. You've got to show how to translate this graph into something else, something that's the input of the other problem. Okay? So the bottom line is that there's that's really sort of what we mean. Remember, we're going to be talking about the distinction between problems and input instances. Okay? And to properly translate or reduce a problem, we've got to give a way to translate all possible instances of one problem into the desired target. Okay, any questions about that? Still nebulous, it will become clearer soon. Okay, one very special kind of problem, okay, which arises a lot, okay, are what we call decision problems. Decision problems just ask you for yes or no answers rather than numerical answers. Okay? So, in some sense, decision problems are simpler than regular problems because obviously if you only got a yes and no answer, that's a smaller, at least that way you can guess right 50% of the time, okay, or something like that. The decision problems are in something simpler than general problems. What's interesting about decision problems, though, is that almost every interesting problem can be converted to a decision problem, just a simple yes-no problem, without really changing it in any interesting way. So what's the point of this? Suppose we wanted to really study the traveling salesman problem. Traveling salesman problem says find the minimum cost tour. Okay? A yes-no question, okay, that is almost as good, or basically the same thing, is saying, given a weighted graph and a bound, k, does there exist a traveling salesman tour whose cost is less than k? So what's the point of this? Here, I've taken the general problem and converted it into a yes-no question. Okay? Instead of saying, what is the minimum cost tour, I've said, is there a tour of less than 50 feet? Okay? What's interesting about that? Well, for just about any problem, you can convert it to a yes-no question. Okay? And since we're going to be interested in translating problems from one problem to another, we're going to want our problems to be as simple as possible. So decision problems that just return yes and no are, by definition, simpler than problems that can return general answers. Okay? So bottom line, we're going to be interested in, from now on, problems that only return yes-no answers. Okay? And try to convert between one and the other. Yes?
So that guarantees that it's easy to map back from the answer of the transfer.
So the question is, does this mean that it's easy to map back and forth from the yes-no question back to the original optimization problem that you might have been interested in? Okay,
no.
Oh, okay, so the question was...
The problem, the Bandersnatch answer is maybe
right.
not the same as the Bobili answer. But if it's all yes and no, then it is the same. And you have no...
Good point. Why do we want these decision problems? Let's look back at the algorithm here. We want to solve Bandersnatch in terms of Bobili. Okay? If the answer to Bobili is a decision problem, what are the possible answers for Bobili? True or false, or yes or no? If Bandersnatch is a decision problem, what are the possible answers? Yes, no. So when we say we're going to return the answer to this, in some sense, the reason why this simplifies our job is the answer translation has already been done. Okay? The answer to this is going to be the same as that because we're going to say, we're going to translate all the yes instances here to yes instances there, and the no instances here to no instances. Okay? By restricting it, it makes our translations easier. Okay? Potentially easier to deal with. Okay? And so that's why from now on we're only going to be talking about yes-no kinds of problems. Okay? How many people accept that? Okay? How many people don't accept that? Okay? Okay, again, the reason that we can do that is that in fact we're not really going to be losing anything interesting. Okay? Because yes-no problems turn out to be quite substantial and can basically do anything that any other kind of problem can. Okay. Let's now talk about a very, very famous yes-no kind of a problem. Okay? This is a problem called satisfiability. Satisfiability is a problem that comes up in logic. Okay? And when we talk about a problem, again, there's two kinds of things we need. We need to specify what the input instance is, what are the arguments to our problem, and the question, what is it that we hope to achieve in this problem? The satisfiability problem takes as input a set of variables, okay, and a set of clauses, okay, over these variables, okay, and asks whether or not there is a satisfying truth assignment for those clauses. Well, what do we mean by a binary variable? Okay, a variable. Each variable in the logic thing is either true or false. That was what you did in logic, true, false. Okay? A logical formula, okay, in logic, you remember, had things like and terms and or terms. Correct? So you can imagine a situation where you had a formula like, let's say, x1 or x2 and not x3. Okay, can't see it. Okay? This is an example of a logical formula, okay, where x1, x2, and x3 are variables. Okay? Is there a way to assign true and false to these variables in order to make this formula true? Okay? How can you do it? Can somebody give me an assignment of variables to this formula to make this thing true?
True, true, false.
One idea is to make it true, true, false. What does that mean? True or true, what is that? True. Not false is what? True. True and true is what? True. Okay? So here we had a logical formula, okay? And there was a way to assign variables to make it true. Okay? The satisfiability problem is exactly that. Okay? Given as input a set of Boolean variables and a set of clauses, okay? Things like this, okay? Is there a way to set those variables to be true? The result of that entire formula to be true? So what are the examples? Suppose here we have a formula where we've got two Boolean variables, and the clauses were like this, two clauses. How do we read a clause? What is a clause? Well, the way to think of it is that a comma represents an and. Actually, a comma out here represents an and. And within a clause represents an or. Okay? Okay? And a bar over something, a complement, means a not. So how would you read this expression? This expression is read V1 or not V2 and not V1 or V2. Okay? Is there a way to satisfy that formula? Okay? What would you have to do to make this formula true? Okay? Is there a truth assignment that we can do? Okay? If we make V1 to be true, this clause will be satisfied because true on something else, okay, whatever it is going to be true, correct, for the or. And here we've got, but if V1 is set equal to be true, what is not V1? So how can we satisfy this clause? Only by setting V2 to be true could we satisfy this clause if this was false. So one possibility is to set V1 equals true, V2 equals true. And then both of these clauses are satisfied. Okay? Meaning that the ands all work out. Okay? So my claim is V1 equals V2 is a satisfying assignment to that particular clause. Okay? So that's why we list, if you think about it, what are we doing? Okay? If we've got ands out here between the parentheses, what we're really saying when we want the satisfiability problem is there a way to set the variables true and false such that each clause contains at least one true literal? Because if these are all ORed together in a literal, in a clause, so long as one of those things is true, the whole clause would be true. And if we're anding together all those clauses, okay, the only way the whole formula can be true is if each individual clause is true. Okay? This is what people call conjunctive normal form, CNF. Okay? Any questions about that? So it's clear you can satisfy this one. What about this formula here? Okay? Here we've got a clause, a set of 3 clauses, again on 2 Boolean variables. If we want to hope to satisfy this clause, what do we know about one of the variables? Okay? What do we know that's going to have to be the case with V1? We hope to satisfy this one. Not V1 has to be true, which means V1 has to be false. You can't see it. Okay, maybe we'll zoom this thing in.
A little bit bigger over the
Sorry about that. Okay, they know. We'll make this a little bit bigger. Sorry about that. Okay? So if we have any hope to satisfy these 3 clauses, what has to be the case? V1 has to be false. Correct? If V1 is going to be false, what do we know about V2? If we have any hope to satisfy this guy, not V2 has to be false, which means V2 has to be false. But if V1 and V2 are false, what happens with this clause? False or false is false. So there's no way to satisfy this clause. Although no matter how hard you try, this formula can't get no satisfaction. Okay? Any questions about that? Okay? Bottom line is, certain formulas can be satisfied, certain formulas cannot be satisfied. And the satisfiability problem asks, given a formula, tell me whether there's a way to set things true or false, such that you satisfy it. Okay? Any questions about what satisfiability is? Okay? Now, the interesting thing about satisfiability is that satisfiability is a famous hard problem. Okay? I can prove to you, in some sense, that satisfiability is as hard as, there's lots of reasons to believe why satisfiability is hard. One reason is because every top-notch algorithms expert has tried to come up with a fast algorithm for satisfiability and failed. So satisfiability is definitely hard in the sense that unless you're smarter than everybody else, you can't hope to solve it. Okay? But it turns out to be actually hard for even a stronger reason, which I don't really want to go into yet. Okay? But even if you forget about the issue of sort of people being smarter or not smart, turns out that you can prove various things about satisfiability. You can actually prove that satisfiability is as hard as, in some sense, any other problem you could possibly hope to solve in polynomial time in a reasonable machine, in a very powerful machine. Okay? Question? Okay, what does NP stand for? What? Okay. There are a couple of acronyms we're going to be using in here, okay, which I don't want to confuse matters too much. NP stands for non-deterministic polynomial. Okay? NP is a set of problems that include all the easy problems that you know how to solve and all the hard and a large set of hard problems that we don't know how to solve. Okay? Speaking in generality. A problem is NP-complete if it is as hard as all the other problems in NP. Okay? satisfiability can be proven to be NP-complete. What does that mean? It is at least as hard as every other problem in this set we call NP, which I haven't defined yet. So bottom line is that you could solve one of those problems fast. You could solve all of those problems fast. Okay? That's sort of the theoretical reason behind why it's not only a question of smarts. Okay? There's a lot of things people have proven that if you could find a fast algorithm for satisfiability, a lot of amazing things would be true that no one possibly believes is true. Okay? So there's very, very good reason to believe that satisfiability is a hard problem. Okay? And in fact, from now on, we're going to take as the assumption that satisfiability is a hard problem. And that if you can prove your problem is as hard as satisfiability, you can at that point drop your hand saying, I can't do it. Okay? Nobody can do satisfiability. My problem is as hard as satisfiability. I'm washing my hands of it. Okay? That's the idea that we're going to be using. Any questions? Okay? Hopefully later we'll go into some of the more theoretical justification for why that's true. But at this point, I think it just obscures detail. Satisfiability is hard, and that's what we got to believe.
So basically, satisfiability problem is the Bandersnatch problem?
Right. So satisfiability from now on is going to play the role of Bandersnatch. Okay? Satisfiability is the problem we're going to be assuming is hard. Okay? And working from that assumption, okay, we can now go on and, and try to prove other problems are hard. Question?
Can we prove that satisfiability is...
How do you prove satisfiability is hard? That's actually an interesting question. The proof requires a certain amount of automata theory. Okay? It's a famous theorem called Cook's theorem. But basically, you prove that anything that can be done on a Turing machine in a reasonable amount of time, in polynomial time, you could do by solving a satisfiability problem. You believe that Turing machines do everything a computer can do, a real computer can do in polynomial time, which is obvious if you believe about Turing machines. Okay? Then this Cook's theorem proves that satisfiability is at least as hard as anything you can do on a Turing machine. Okay, in a reasonable amount of time. Okay? So maybe I don't want to go through the details of that right now. Okay? This is something I want you to take on faith. But this is something I'm not trying to hide. This is a very, very clear and, it's a very nice proof. Okay? That you can prove that, in fact, satisfiability is as hard as anything else in NP. Any questions? Question?
I mean, a valid input would be something where every variable is used only once, right?
So one valid input for the satisfiability problem you're saying would be a case where every variable is used only once. Okay? So you're saying for the satisfiability problem, one potentially valid input would be, a formula would be x1 or not x2. Something like that. Okay? Yeah. That would be a perfectly valid satisfiability problem, even if every variable appears only once. Then you may say that doesn't sound very hard.
No, I'm saying if you have n those independent variables,
yeah,
you have 2 to the n possible assignment statements.
Right. So now why?
Exponential.
Right. So why is it that satisfiability? Let's think intuitively. Why is it that satisfiability isn't trivial to solve? If you've got n variables, if you want to go through all possible solutions, how many possible solutions are there to a satisfiability problem? How many possible truth assignments? 2 to the n. So a backtracking brute force algorithm would be try to satisfy it by doing all 2 to the n possible solutions. Trouble is 2 to the n is exponential. Okay? If you find a way to avoid doing an exponential number of them, come back and we'll talk. Okay? But you're not going to find it. Okay? Because satisfiability is provably hard. Okay? Any questions? Okay, now that we know about satisfiability, let's look a little at what was the problem of the day. Okay, what was the problem of the day? The problem of the day asks, give a polynomial time algorithm, okay, to satisfy Boolean formulas in disjunctive normal form. That's DNF, not CNF. What did conjunctive normal form formulas, the kind we said satisfiability were hard, look like? They were a bunch of clauses with or, Okay, separated by and out here, correct? This was what we meant by conjunctive normal form, right? What is disjunctive normal form? Disjunctive normal form, if you remember from your logic, simply means that they reverse the roles of the ands and the ors. So what does a disjunctive normal form formula look like? Looks something like this. And, or. And, or. If I give you an expression written like this, how would you come up with a way to see if there's a way to satisfy it? What is true about an expression written in this DNF? If it's satisfiable, what do we know?
It's enough to satisfy one of the rows.
It is enough to satisfy one of these clauses in DNF. Why? Because if you satisfy this, since everything else is getting ORed together, satisfying one of these satisfies the whole formula. Correct? How would you test whether you satisfy this thing? Under what condition can you satisfy something that's all ANDed together? If I have an expression x1 and not x2 and x3, how would you satisfy that? What would you have to do with x? 1. Set it to be what? True. What we have to do with x2? What would we have to do with x3? So you're saying that from reading from left to right, you can tell how you want to set the variables here, right? Is there any way a DNF formula might not be satisfiable?
If the same variable appears twice and one of them is the negation.
Exactly. If you have x1 and not x1, now you're in big trouble. Because now you can set this to be true, but then this is going to be false. And if you set this to be false, then this is going to give you trouble. So long as all clauses do not contain a variable and its complement, in disjunctive normal form, satisfiability is easy. Okay? It's in conjunctive normal form that satisfiability is hard. Question?
What if they do?
What if they do? What if, excuse me, what if?
You said that
What if they contain both a variable and its complement? How would you satisfy V1 and not V1? Okay? V1 and not V1. We can make that true. So on each clause, if a variable and its complement appears in each clause, then there's no way to satisfy it. Unless that's not true, there is a way to satisfy it. So algorithmically, you can answer the question, is there a way to satisfy it quickly? Yeah.
each conjunctional form has a conjunctional form, and translation is done at a normal time. And we've proven that the CNF is hard.
Okay. Interesting question now. DNF, we know how to solve satisfiability easily. CNF, I'm telling you it's hard. When you took logic, okay, you probably learned how to convert between CNF and DNF. Why couldn't you solve satisfiability in CNF by taking the DNF, taking the CNF, translating it to DNF, and then solving it here? The reason is because the translation might take exponential time. Why is that? Remember what the translation, I don't know if you remember this, what was the procedure to translate between CNF and DNF? It was like multiplying out the number of terms, correct? So if you started out here with, let's say, 3 variables in each one of these things, multiplying 3 by 3, you ended up getting 9 terms. And then multiplying it by 3 more, you got 27. you know, 81, dot, dot, dot. The point is that when you multiply and you do that translation, you're going to be creating an exponential number of terms. So in fact, the reason why that translation argument doesn't work is because the translation takes too much time. Okay? If you go through that actual process, you'll be able to convince yourself of that. That's why it does work. Okay? Any other questions about this? Yeah?
So you could argue that you can't find one because there's no translation, there's no polynomial translation?
What I'm saying here, okay, what am I saying? A CNF formula, DNF formula, can be solved in time polynomial in its size. I have proven earlier, okay, or Cook has proven, that CNF cannot be solved. Essentially has proven that CNF cannot be solved. Now, why doesn't one imply the other? Basically, what we've proven is if you want to convert between one of these and one of those, the translation would have to take exponential time. That's really what we've proven. Okay? Any questions? Okay. Let's get down to doing translations. Okay? What is an example of a translation? Let's look at a second problem. A problem called 3 satisfiability. What is 3 satisfiability? It's a variation of the problem called satisfiability, which you're now familiar with. In 3 satisfiability, the problem is exactly the same as satisfiability, except that we are limiting each clause so that each clause contains exactly 3 literals. What does that mean? That means you can have a clause that says V1 or not V2 or not V3, but you can't have a clause that looks like this, and you can't have a clause with a 4th symbol in it. Every clause is now limited in length to being of length 3. Okay? You still want to do a satisfiability. You've given a CNF formula where each clause contains 3 items. The question now is, does such a clause, such a formula, satisfiable or not? Okay? Now, what's the result of putting this limitation on the problem? Let's think about it. Certain satisfiability problems most satisfiability problems in some sense had long clauses in there. We've proven satisfiability is hard, but those hard problems include the problems that have long clauses. Maybe satisfiability is easy if you use a short enough clause. For example, suppose each clause contained only 1 literal in it. Okay, so now we add a thing where each clause contains 1 literal. And we're going to AND them together. That would be 1 satisfiability. Is 1 satisfiability a hard problem? Okay.
No, it more or less takes only linear time.
1 satisfiability is a trivial problem. Why? How would you satisfy the clause V1? Okay? You have to set V1 to be equal to true. You don't have any choice in the matter. Now you take a look at this thing. You have not V2. How do you set that clause to be true? V2 is false. A clause, if we have a 1 satisfiability formula, what's the only condition under which we won't be able to satisfy it? Okay?
That different clauses have the same variable and one is negated.
If there is some clause of the form VI and some other clause of the form not VI. So 1 satisfiability is a trivial problem. Arbitrary satisfiability is a hard problem. Somewhere in between would be 3 satisfiability, where every clause is now, instead of being limited to 1 where it's easy, we let every clause be limited at 3. And the bottom line question is 3 satisfiability hard or not hard? Okay? Any questions about 3 satisfiability and how it differs from satisfiability? Okay, yes?
no, just with terms. If you say a problem is hard, you mean it is belongs to NP complete.
Right. When I say a problem is hard, that means I mean it's NP complete. Okay? That's what it'll mean in the course of the class discussion. Yeah.
Why don't check do satisfiability instead?
Well, why don't we first see, turns out 3 satisfiability, okay, we can prove is NP complete very easily. Okay? 2 satisfiability turns out to be an interesting case. Okay? Let's look at the 3 satisfiability problem. My claim is 3 satisfiability is NP complete. How would I prove that 3 satisfiability is NP complete? I need to go through my Bandersnatch reduction. What problem do I know is hard? Satisfiability in all its glory is a hard problem. What is going to take the role of the mobility problem? Okay, if I want to prove 3 satisfiability is hard. Three satisfiability takes the role of the mobility problem. So what do I have to do in order to prove 3 sat is hard? I've got to convert arbitrary satisfiability problems into 3 sat problems. Okay? How do I go about doing that? I need to give a translation. What I'm going to do to prove that it's hard, okay, is to translate my sat problem into a 3 sat problem, 1 clause at a time. Okay? How big are the clauses in the 3 sat problem? How many literals do they contain? How many, if I have a particular clause in the sat problem, how many literals does it contain? Some number from 1 to n. Okay? Because if it contains a literal more than once, okay, I might as well just delete the extra copy. Okay, since there's n variables, the only interesting literals in a particular clause are going to be the distinct copies of it. Okay? So what I'm going to do is now do my translation based on size. Suppose that a clause CI from the sat problem contains k literals. If it has 1 literal, that means that my clause from the sat problem looks like this. Okay? I now want to create clauses where each clause contains 3 literals. Okay? Such that if this is satisfiable, the other one is going to be, all 4 clauses will be satisfiable. And if the other thing is not satisfiable, this new thing is not going to be satisfiable. So what's my translation going to be? I am going to create 2 brand new variables, only in my 3 sat problem, called v1 and v2, and I'm going to create 4 clauses. All these clauses contain z1, the variable that we inherited from here, and it contains all possible combinations of the negation of the other 2 new variables I added. Okay? So both true, 1 true, the other true, neither true. What is true about these clauses? If I want to make all these clauses true, what do I have to do? If I set z1 to be true, this is going to be true, and this is going to be true, and this is going to be true, and that is going to be true. Suppose z1 is false. Can this clause be true? Well, yeah, it can, because I could set both of these to be, one of these 2 to be true. If z1 was false, can this be set to be true? Yeah, by setting one of these to be true. But what's the point? I've got all 4 possibilities of these 2 new variables, correct? Is there any way that I can set v1 and v2 to be true and false, such that all 4 combinations of it and its complements, that all 4 of those are true? No. Okay? How many people see that? How many people do not see that? Okay, good. So the bottom line is that by doing this translation, this clause will only be satisfiable if if Z1 was true, this is satisfiable and all of these are satisfiable. If Z1 was false, the answer was going to be false, and the answer to our 3-sat problem will be false. Okay? Any questions? What if the clause we had contained two variables, Z1 and Z2? What I'm going to do is now create a brand new variable, V1, and two clauses, each of which have 3 literals in it. Okay? The old two variables and V1, not V1. If there's a way to set these two to be true, my claim is that both of these can be satisfied, correct? If both of these were false, is there any way both of these can be made to be true? No, for the same reason as before. If we want to make both of these true, we'll say, okay, let's make V1 to be true. That'll cover up for these guys, but not over here. Okay? So here we translated a clause of size 2 and created two clauses of size 3. Okay? Again, the truth here preserves the truth there. What if we have a clause of size 3? Well, we want to get clauses of size 3, so we don't have to do any work at all. Just copy that guy into our new problem. The only remaining case, okay, is what if we have a clause that has more than 3 literals? That's presumably the hard one. What we need to do is to chop this thing up into pieces such that each piece is exactly 3 literals in size. How are we going to do that? We are going to create a set, if we have n literals in this clause, we're going to create n minus 3 new variables and n minus 2 new clauses to replace it, where each clause is going to look like this. The first clause is going to contain Z1, Z2, and the first of our new variables. Okay? So it would look like Z1, Z2, V1. That's going to be the first of our new clauses. Our second clause is going to contain the complement of our new variable, the third variable from that clause, and our second new variable. And what we're going to do is, for every one of these new guys, we're now going to create, except for the first and last one, every one of our new clauses is going to contain exactly one of the old literals. Okay? Flanked by the complement of that and the complement of the next one. So what have we done here? We've built a chain of taken our one big clause and built a chain of little clauses. Correct? This clause is linked to that clause by what? By this new variable we added. True here, in its native form here, complemented here. The second and the third clauses are going to be linked by complement of V2, Z4, V3. Okay? What's the purpose of this translation? First of all, any questions at this point? What's the purpose of this translation? There's something very beautiful to it. Okay? What if all of these guys were false? Okay? Suppose Z1 and Z2 was going to be false. If we wanted to hope to satisfy this, what would we do? We'd have to make V1 to be true, right? That would mean that this guy is false, correct? Because this is the opposite of the true. If all of these were false, this would be false. What would we have to do to save this clause? We'd have to set this guy to be true, which would make this guy to be false, false. We'd have to save it by using our extra one. What is the last one of our clauses going to look like? Complement of Vn minus 2, Zn minus 1, Zn minus 2. Zn, excuse me. What's the point of that? This guy would have been false. This guy would have been false. This guy would have been false. We've run to the end of the line. If all of these guys were false, there was no way to make all of these guys true. Correct? Okay? Because we're sort of forcing the issue. We can push the issue far away, keep delaying it, but we eventually got to pay the piper. And by the last clause, there's no way that we can push off our problem anymore. At least one of these clauses would have to be false if the original clause was false. How many people believe that? Okay, how many people don't believe that? But what if this clause was in fact satisfied? What did that mean? There was at least one guy that was true. One of these z variables was true. If that's true, okay, then somewhere in our long chain of clauses, somewhere here we've got a central piece that is in fact true, which means that we could set our new phony variables flanking it to both be false, correct? If in fact that center z was true, this clause will be satisfied even by setting both of the other guys to be false. And that said, we can now ripple in that direction and in that direction, making sure that one of the new variables we added will be true in every single clause. So if there was one correct true here, we can satisfy all the new guys. If there was none of them, all of them were false, we cannot. Okay? And we've done this translation. Any questions at this point? So what's the magical thing that we've done? We've taken as input a set of variables and a set of clauses of arbitrary sizes. We've translated it to the point where we got a set of clauses and variables, more variables and more, but not many more, okay? Such that the original assignment, if the original thing is satisfiable, the second thing has to be satisfiable, and vice versa, okay? My claim is I've translated any SAT problem to 3-SAT. The answer to the two problems has to be preserved. I've just proven that 3-satisfiability is at least as hard as okay? Satisfiability, 3-SAT is hard. QED. Any questions at this point? Okay? Question?
Do you have to say anything about how long the translation took?
Okay? How long did the translation take? What was the input to my problem? Okay, let's figure out how long that translation takes. Because you're right, I have to describe my translation. My original problem, my SAT problem, contained how many variables? N variables and M clauses. Correct? What's the maximum number of literals per clause that I had? Less than or equal to N literals per clause. How much time does it take to translate a clause from SAT to 3-SAT by my translation? If my original clause had at most N literals in it, what I took was a clause which had at most N literals in it, and I produced something that contained n minus 2 clauses. Okay? Sorry about that. And I added, at most, n minus 3 variables. So how much time did it take to translate one clause into this thing? Okay? So you may say 2n minus 3 or something. It's clear that it took a linear amount of work. I've changed the size of this from this to this by a linear factor. Okay? My claim is at the end of this thing, what am I going to have? I'm going to have my 3-sat problem. We'll have at most how many clauses? My original thing had m. For each clause, original clause, I was going to create at most n other clauses. So that I have at least that many, at most that many clauses, because each one might take at most n. How many variables would I have? In the original problem, I had n variables. For each clause I translate, I might create another n variables. The total time to do the translation is clearly polynomial. Presumably it's linear in the size of what I'm actually doing. But I don't even need to be that precise about it. It's very clear that in doing this translation, it's a fast operation. It's a polynomial time operation. Okay? Thus, my translation is fast. Okay? And I have preserved correctness. Okay? Thus, if the regular satisfiability is hard, 3-sat has to be hard. Okay? Any questions about that? Okay? How many people see where the correctness of the translation comes from? Okay? How many people do not see that? Okay? So what's interesting about it? We've proven that 3-sat is hard. One question that we were asking, that I already got asked, is what about if I have 2-sat? 1-sat is easy, 3-sat is hard. What is the case for 2-sat, where every clause contains 2 literals in it? That, it turns out, can be done in polynomial time, but it's kind of a tricky algorithm. So it's not something that's so obvious as the case for 1. Okay? Question?
How come we can't translate in the same fashion?
Why can't, now the question is, well, why can't we do the same translation to prove that 1-sat is hard, that 2-sat is hard? Let's look at the translation. Okay? Where do we have problems? The big problem is going to be not with the case of k equals 2, not with the case of k equals 1, but the problem's going to come up in the big translations. What did we do with each clause in the resulting thing? We produced a chain of clauses where every clause contained one original literal, it contained one back guy and one forward guy. To produce this chain, you needed to point above and beyond, okay, which took 2 literals right there. In order to put a data field, in some sense, into the clause, in order to make that clause do something, you had to have something that was true or false about it before. So this translation doesn't work for 2-sat because there isn't room for everybody to be there. How many people believe that? Okay, how many people don't believe that? Question. Just don't believe it.
Why? We don't necessarily have to use the full set problem.
Now you're saying I don't necessarily have to do my translation this way, and you're right. Okay? But I can give you a fast algorithm for doing 2 satisfiability. Okay? So I can prove that 2 satisfiability is in polynomial time by giving you an algorithm. If you were to give me a way to solve 3 satisfiability using 2 satisfiability, that would give you a fast algorithm then to solve 3-sat. If you come up with a reduction from 3-sat to 2-sat, I want to talk to you. Okay? because you would have come up with a fast way to solve satisfiability. Okay? This doesn't work. Maybe you've got a better idea, but I don't think so. Okay? Because that would imply that this guy is reasonable. Okay? Any questions about that? Okay? Now, what is actually, okay. So the interesting thing about this is that 3 sat is hard because every clause contains 3 literals. Once you have 3 or more literals is where satisfiability gets to be hard. Now, what's interesting is we've proven that 3 sat is hard now. From now on, we don't need to use full satisfiability as a hard problem. If we want, we can use 3 sat. And it's every bit as hard as the original. For technical reasons, it usually makes life a lot easier to do our translations from 3 sat. Why is that? 3 sat problems are nice and simple. Every clause contains exactly 3 literals. You have to write, in doing your reductions, a translation procedure. Which is it going to be easier to write a translation procedure? From the full glory of satisfiability to some problem, or some nice special case of 3 sat to another problem? Which will you have to do less work in doing the translation? Okay? From the simpler problem. So from now on, we're usually going to use 3 sat instead of satisfiability. But because it's hard, we haven't lost anything. Okay? Any questions about that? Okay? One other thing to notice about the reduction, which I'd just like to make clear, is that we did notice that we did not solve the problem in the course of doing the translation. All we did was take each clause, x1, x2, x3, and translated that to another clause. The work of our algorithm was that of translation, not of actually solving it. I didn't care what satisfying assignment this was. Okay? I didn't need to know. If I needed to know what satisfied this, I already had a solution to my problem. The bottom line, these translations are reformatting. Okay? Any questions? Okay? That's what we're doing, is we're reformatting problems. Any questions? Okay. That said, let's well, I'm just trying to think whether we have to. Okay. That said, let's try one quick. Try to make some distinction here between something that people have started to brush up against. Okay, and is somewhat confusing. This whole idea of proving things hard, the key idea is doing these reductions, these translations. That is an intuitive idea that I think people can really get a handle on without knowing a lot of theoretical machinery. Okay? But when you start studying NP-completeness, start studying this hardness problem, there are some technical notions that come up, okay, that we've heard people ask about. What's NP-completeness? You know, what does it actually mean to be complete rather than hard? Okay? I don't really want to go too much into the detail of this, because I think actually this obscures more information than does sort of just thinking about things in terms of translation. Okay? But what is actually the distinction here? Okay? We're going to be talking about the difference between P problems and NP problems. The problem is in P if it can be solved in polynomial time. Okay? Shortest path is in P. Minimum spanning tree is in P. Sorting is in P. Okay? Everybody is in P if they can be solved in polynomial time. That's what we mean by problems that are in P. In an ideal world, every problem would be in P. Because if so, then we would have a fast algorithm for every problem. Okay? But we do not live in an ideal world. We say that a problem is in NP is a problem that maybe we can't solve it in polynomial time. But if somebody were to tell us the answer, we could check whether they were right in polynomial time. So let's think about it. You're taking an exam. Okay? You look at a problem, you don't know how to solve a problem. Okay? You look over at your neighbor. Okay? Your neighbor has the answer to the problem. Okay? You couldn't get that problem, the answer yourself, or else you wouldn't have been cheating. Okay? But now you look at this person's answer. Before you write it on your paper, you're going to want to convince yourself, is that answer correct? Convincing yourself that an answer is correct is often easier than getting the answer yourself. Correct? For example, if somebody were to give you a satisfiability problem and say, here is a set of clauses, show me how to make that thing true. You would look at that and say, oh, I don't know how to do that. I have to look at all possibilities. But if on the other hand they said, okay, look, T1 is going to, V1's false, V2 is true, V3 is true, V4 is false, dot, dot, dot. How would you convince yourself whether or not they're right? Okay? You could take a look at each clause, take a look at their answers and saying, well, we got a true guy in this one, yeah. True guy in the second one, yeah. True guy in the third one, yeah. It's easy to check if the answer is right once we have it. It's hard to actually find what the answer is. Okay? So that's what the distinction is. A problem is an NP. Okay? If it is very easy to check the answer once somebody gives it to you. Okay? A problem is in P if it's easy to actually find the answer from scratch. Question?
So what if I have a decision problem where somebody tells me, well, my answer is there is no possible
Okay. So the question now is, what about a decision problem where they come back and they give us an answer of yes or no? Okay? You can't come back taking a look at from the yes or no and go back to the real to check that necessarily.
Even if it was a satisfiability, if he says this
Okay.
is not satisfiable.
The truth is to see that the answer is satisfiable. For example, in satisfiability, if somebody comes back with a no answer, saying there's no way to satisfy it, you're right, you don't have any way to check that answer easily. But on the other hand, if they come back with a yes answer, it's possible to check.
Yeah.
So in fact, to be technically right, it's an NP only if you can check the yes answers. You don't have to check the no answers. Okay? Question?
So what does NP
And a problem we say is NP-complete if the problem is hard and the problem is in NP. Okay? This is just terminology here. We say that a problem is in NP if there's a way to check the problem. Okay? If someone gives you the answer, to check the answer quickly. We say that a problem is hard if it's at least as hard as every problem in NP. We say that a problem is complete if it is also, not only is it NP hard, but it is also in NP. Okay? If you're not getting these definitions, don't worry about it. Okay? This is not, I don't want to confuse people. Okay? But what's sort of the ideas here? A problem that was in P was, is there a shortest path in the graph from S to T? Okay? Or a decision problem would be, is there a path from S to T in the graph of length less than K? That the answer is yes or no, it's a decision problem. That, using Dijkstra's algorithm, you can do in polynomial time. That would be a problem that's in P. What is a problem that is an NP? Is there a traveling salesman tour, okay, of length less than K? Okay? How could you prove, if I gave you a traveling salesman tour, could you convince me, could I convince you that I was right? Well, I say, look, I have a tour that is less than K, total cost. How could you check it up? Well, you could go through all the edges, okay? And for each edge on that tour, add them up. If that total is less than K, then I got to say you're right, you got a tour. Okay? So it's easy to check, but it's hard to find. Any problem that is easy to check is an NP. Any problem which is easy to solve is in P. Any problem that is easy to solve, by definition, is easy to check. So there are more problems in here than in there. Okay? So when we say a problem is NP-complete, what we mean is that it's at least as hard as every problem in NP. Okay? And that's where the strength of the satisfiability result is. Because with satisfiability, you can prove it's at least as hard as every problem in that class. Okay? So satisfiability is a hard problem. Any questions about the distinction between P and NP? Okay, question.
Could you draw little circles for the...
So the standard sort of model, if you sort of look in a book, you'll see that there are problems. You just have sort of a Venn diagram, a set of problems. Here you've got P is a set of problems you can do efficiently. NP is a set of problems that you can guess that you can check the answers efficiently. NP-complete problems are problems that are in NP, which are as hard as everything else in NP. Okay? So presumably, no NP-complete problem is in P. Because if the hardest problem could be done in polynomial time, all of them could be done in polynomial time. Yeah. But P is in NP because to actually, you know, it's sort of like this thing. If you know how to solve the problem, you certainly know how to check if somebody else gives you the answer if it's correct. You just say, is your problem answer the same as they got? Okay? So P is within NP. The NP-complete problems are presumably sitting someplace here. Okay? Again, there's some technical reasons why, you know, this picture, you know, there's certain assumptions being made here. Okay? But in general, this is the way I think the world is. Yeah?
The NP is hard to solve problem.
NP problem is any problem which it is hard, which you can prove that somebody else's answer is correct efficiently. So just because a problem is in NP doesn't mean, okay, that that the problem is necessarily hard. Okay? For example, given an arithmetic formula, figuring out whether the answer is equal to this, okay? That is a problem in NP. You give me a set of formulas, an arithmetic formula, and you give me an answer, and you ask me, do these numbers add up to that? That is a problem in NP. Why? Because I could check it very easily. That's actually P. Okay, but I could check that very easily. Okay? It doesn't necessarily mean that it's hard. Okay? Any questions? Yeah.
Are there any examples of problems which are in NP but not in P or in NPC?
Then there's questions. The question is there any problem in NP which is not here or not here? That's a famous problem.
Okay.
Okay?
Is there even something outside from NP?
Is there even anything? Is P any different than NP? That is a famous problem.
Yeah, okay. No, but is there something outside of NP?
Is there something that is not in NP? Mm-hmm. The answer is yes. Okay? What's an example of a problem that's not in NP? Suppose I ask you how many traveling salesman tours there are of length less than k. Suppose I look at a graph and I tell you there's 756,332 traveling salesman tours less than k. How can you check that? Okay? There's no way you can even check that answer in polynomial time. You may say, well, let me give it to you by writing out all the tours. But that's an exponential number of tours. Okay? I couldn't write out my proof in polynomial time. So this is an example of a problem that's not in NP. Okay? Any questions? Okay, it's a problem in P, a problem in NP, a problem not in NP. Okay? What's the most important thing to take home from this? Don't let it confuse you. Okay? This is something you guys kept insisting. What is NP-complete? What is this? Okay? The terms come up a lot. The most important thing, the only thing that I'm really, really concerned about you knowing, okay, is this idea of how you prove that a problem is hard. by doing a reduction. That's the interesting solid thing. A lot of these other distinctions are fairly technical, require a certain background in orthometer theory, okay, to really get them solid. Okay? The solid thing to get down is how do you use a reduction to prove things hard. Okay? And we'll look at more examples of hardness in the next couple of classes. Okay, one thing before you go. The next problem of the day, because I've sort of gotten a little bit behind. It might be easier, actually I even got further behind than I thought. It might be easier to actually do this problem next time rather than that one. Okay, but we'll talk about it. So reverse the next two problems of the day. We'll talk about it next week. Okay, thanks for your attention. Take care. I'll talk to you later. Bye.